Earlier, we proved that the Markov property has a strong version, where Markov chains have the same kind of restarting behavior even if you stop at a random stopping time. In this lecture, we're going to prove two key results about martingales that are of the same flavor, dealing with what happens when you stop, sample, or condition a martingale at a stopping time. In order to understand how that works, we're going to develop what you could think of as a simple model for buying and selling stocks in a stock market exchange in order to develop a new tool for testing whether something is a martingale or producing new martingales from old ones. So here's our simple model. A stock evolves in time. Let's let xn denote the price per share at time n in a discrete time situation. You, the investor, would like to buy some number of shares, let's call that U shares of the stock at some time s, and then sell them at some time t later on. Of course, you would like to make a profit in doing that, so you would hope to sell them at a later time when the price is higher than at the earlier time. In a future lecture, we'll discuss some strategies for trying to maximize that expected profit, which will lead us to some more key results about martingales. But for now, let's just deal with the simpler question of how do you calculate the profit or loss that you incurred during this process? Well, if xt is the price of the stock at the end time t, and xs is the price of the stock when you buy it, that means that the total amount of money that you make or lose, depending on the sign of this number, is u times xt minus xs. That is u times the increment. Now we can do one simple telescoping calculation here, which will help us understand a different way to do the same thing. We could write xt minus xs as xt minus 1 plus xt minus 1 minus xt minus 2 plus etc. down to xs plus 1 minus xs. And now, if we distribute this product by u through these increments, then we have a different interpretation of the same process. Instead of buying u shares at time s, hanging on to them, and then selling them at time t, we could buy u shares at time s and sell them at time s plus 1. Then buy u shares at time s plus 1 and sell them at time s plus 2, all the way down the line until time t, and that will accomplish exactly the same goal, assuming that there are no fees associated with the buying or selling of the shares. This is not a very realistic model. Now this points out that maybe we don't want to buy at the beginning and sell at the end and do nothing in between. We could actually make changes at every time step if we want, and this is just a special case of that. So let's put those things together. We might have a sequence un of trades. Un is an amount of stock that we buy at time n minus 1 and sell back at time n. Now if we do that over time, from the start time until some time n, how much profit have we made or loss have we incurred? Well, we just have to add up all of those increments. The amount that we buy at time j minus 1 and then sell back at time j times that increment is the amount of profit or loss during that time step, and we add those up over all the time steps up to time n. We might write this increment as delta xj. We're going to refer to that sum as in of u and x. And I'm denoting it I because it's a simple model of a kind of integral. We call this a stochastic integral. If this were a Riemann-Stieltjes integrator function, then this would be the definition of the Riemann-Stieltjes integral of this simple function here on the interval from 0 up to n. Now, thus far, everything here is deterministic, but of course, in reality, this process xn is going to be random. And this process u might also have some random component to it. So this will be a random variable as well, and we'd like to understand what kind of stochastic process it is as we vary n. At the same time, we also might want to note that our strategy could involve factors that are not at deterministic times, like s and t, but rather might depend on values of the process up to that time. For example, we might not want to buy at a fixed time s and sell at a fixed time t, but rather buy at a random time sigma and sell at a random time tau, where those are, for example, sigma is the first time that X drops below $5 per share. And tau is the first time that X goes above $10 per share. If we do that, then we're guaranteed to make a $5 share per profit, provided we actually can wait until that happens. Now, if the process is random, then these will be random times, but as you can imagine, they are stopping times. And we can actually fit this into the model of the stochastic integral that we wrote on the last slide if we take our trading strategy uj to be the following. That is, uj is either 1 or 0, and it's 1 if and only if j is in between sigma and tau, which is a random variable here. Alternatively, we can write this as the indicator of the stochastic interval from sigma up to tau at j. And to be very precise here and highlight the randomness, what we mean here is this is the indicator of the event of all those omega, and we'll append a j in here such that sigma of omega is less than j is less than or equal to tau of omega. That is a stochastic interval. Not to be confused with stochastic integral, although the two are closely linked. We usually only call it a stochastic interval if the sigma and the tau are stopping times, because we have lots of tools for dealing with them in that case. Now, in any case, if we take uj to be this indicator function here, we buy 1 share of the stock at each time j in between sigma and tau, then uj on the event that j is less than or equal to n, we could write instead like this. That's the indicator of the stochastic interval from the minimum of sigma and n up to the minimum of tau and n at j. And therefore, this stochastic integral in, which just measures your total profit or loss up to time n, employing this trading strategy, is going to be the sum, j going from 1 up to n, of that indicator times the increment. And now this is a telescoping sum, exactly as we've usually handled it, except that we're summing up over a random interval. We're just summing over those j's that start at sigma and go up to tau, min with n, but that min with n won't matter since we're actually summing over j going from 1 up to n at front. And so this telescoping sum will exactly equal x tau min n minus x sigma min n. So that's the amount of profit that we make here. And the only issue is, well, we really wanted it to be arranged so that we got $5 profit guaranteed. That's not guaranteed here because if we stop at some particular n, we may not have reached that threshold yet. So we may have to wait arbitrarily long for that to happen. In fact, it might never happen, but let's assume that sigma and tau are finite stopping times almost surely. In that case, at least formally, we can get the result we want by taking the limit as n goes to infinity of that. And since x at time tau is at least $10 and x at time sigma is at most $5, that will for sure be greater than or equal to $5, as we'd like. This kind of buy low, sell high strategy you might think of as a very simple and commonplace strategy for trading on a stock. But we'll see in a near future lecture that it's actually not a very good strategy, and it's better to be bold. But we'll come to that later. For now, I'd like to understand probabilistically what kind of process this is in that case. We've just been discussing stopping it at some stopping times, and so we'd like to have some nice properties of this stochastic process in order to understand the stopped version of the process. And here's the key point that will help us to understand and prove what those properties are. What kinds of trading strategies are even allowed here? What I'd really love to do is not sell on a day when the stock reaches a certain high. I want to sell the day before the stock crashes. or I want to sell on the day that the stock reaches its global maximum in price. The problem is that I can't do that without a time machine. Those events, the day before the stock crashes or the day that the stock reaches its absolute maximum price, those require knowledge of what the stock will do in the future. And in a realistic model, my trading strategy can't do that, unless I'm in the inner circle or the CEO of the company. And then I have a little bit of future knowledge, but if I use it, I'll probably go to jail. So we would like to assume that our process, UJ, describing our trading strategy, cannot see into the future. In particular, UJ is the amount that we decide to buy before the jth price is set. It's made based on what happened up to the j minus first value of x. So that is to say, if we let Fn be the sigma field generated by the process x up to time n, Uj really needs to be Fj minus 1 measurable. Now that means that it's Fj measurable since Fn is a filtration and so is increasing, but it's better than adapted. It's adapted to one time step earlier. We call such processes predictable. To be precise, given a filtered probability space, a process Un is called predictable if for each n, Un is Fn minus 1 measurable. For example, Un could be taken to be any function of the steps in the process x up to time n minus 1. And that function can, of course, vary as well. This will be an Fn minus 1 measurable process. And if the sigma field you have in the filtration is generated by the process x, then we also know from the Doob-Dinkin representation that all predictable processes will have precisely this form. Okay, so now we have a handle on what kinds of trading strategies UJ are allowed. They're the predictable processes. But what do we know about Xn itself, the process that describes the stock price? Well, the stock price is the result of a bunch of people trading. It's based on a whole bunch of different people playing a betting game. That gives the total valuation of the company's assets, and then the stock price is some fixed fraction of that based on how many shares the company puts into the market. So, all that being said, if all of those betting games are fair games, or if they're at least fair in sum total, that means we would expect the fluctuations in the price to be described by a martingale. Now, that may not always be a realistic assumption, but for our purposes, that's what we're going to assume here, since we're actually interested in using this setup to understand martingales better. So we're going to assume that it is a martingale. We can be actually more generous than that and only assume that it is a sub-martingale or a super-martingale, as long as it's one of those. If we then have a predictable process U, and in the case where we only know that Xn is a sub or super martingale, we better assume also that U is greater than or equal to 0, then this process In, which describes our amount of profit or loss at a time n, which is this discrete stochastic integral, that is also a martingale. We're building a martingale from this martingale here using this predictable process. That's in the case where Xn is a martingale. If Xn is a sub-martingale, then Zn is also a sub-martingale, and if Xn is a super-martingale, then Zn is a super-martingale. Again, that requires the assumption that Un is non-negative for those second two statements. The proof is very straightforward. Let's just look at Z at time n plus 1. By definition, that's Zn plus the next increment, Un plus 1 times delta Xn plus 1. And therefore, if I condition that on the information up to time n, I get Zn conditioned on time n plus conditional expectation of Un plus 1 times Xn plus 1 minus Xn conditioned on time Fn. Now, Un is a predictable process, which means that Un plus 1 is Fn measurable. So we can pull that outside the conditional expectation. And so therefore, this term here is Un plus 1 times the conditional expectation of Xn plus 1 minus Xn given Fn. Now, if Xn is a martingale, this is 0. If Xn is a super martingale, this is less than or equal to 0, and if it's a submartingale, this is greater than or equal to 0. And given the sign of un is non-negative here, what that means is that this whole term here is either equal to 0, greater than or equal to 0, or less than or equal to 0, depending on whether x is a martingale, a submartingale, or a supermartingale. And so we just have to look at this term here to see what this is equal to. But notice that Zn is a sum, j going from 1 up to n, of uj times xj minus 1. uj is a predictable process, and so this is fj minus 1 measurable, as is this, because it's adapted, and this one is fj measurable. So that shows that this whole term here is certainly fj measurable for each j, and we're adding those up to n, which means that Zn is fn measurable. And that means that this term here is just equal to Zn. Thus, this conditional expectation of Zn plus 1 given Fn is just Zn plus a term here which is either 0, greater than or equal to 0, or less than or equal to 0, which shows that Zn is a martingale, submartingale, or supermartingale accordingly, concluding the proof. Actually, a kind of converse of this is also true and is an effective tool for deciding whether a certain underlying stock price process is a martingale. Here's the statement. Suppose that we have an adapted process xn that we'll assume is L1, and suppose that for all bounded predictable processes, un, we get that the expected value of this stochastic integral is equal to 0. That's what would happen if we knew that x was a martingale, by the way, because all of those delta x's have expected value 0 for any martingale, and the predictability of this allows us to pull it outside the conditional expectation term by term, as we did in the previous proof. So we get that the expected value of any stochastic integral against a martingale integrator is 0. Suppose that we know that this stochastic integral has 0 expectation, but we don't yet know that xn is a martingale. Well, then it turns out that it is a martingale, if we know that this is 0 when integrated against every bounded predictable process. And moreover, if we only know that this is always non-negative, then we get that xn is a submartingale. If we only know that it's always non-positive, then we get that xn must be a supermartingale. Although to get those last two conclusions, we again want to assume that our trading strategy U is a non-negative process. So the proof here in the martingale case works just like we had on the previous slide. Remember, we showed that the conditional expectation of this at time step n plus 1 is the same as its value at time step n plus this term right here, un plus 1 times this conditional expectation of xn plus 1 minus xn given fn. Now let's take expectations of both sides. And that tells us that the expectation of in plus 1 of u and x is the expectation of in of u and x plus the expected value of un plus 1 times this conditional expectation. Now, if we are looking at the martingale case, if we assume that this is equal to 0 for every n, that means that both of these two terms here are equal to 0. And so what that tells us is that for every bounded predictable process un, this expected value here is 0. So we can take a particular un plus 1 there to make this a helpful statement. If we take un plus 1 to be the signum of that term in there, the conditional expectation of xn plus 1 minus xn given fn. Well, notice that that is a bounded process. Signums are between -1 and 1. And because this random variable is fn measurable, that shows that u is a predictable process. So, by what we had above, that means that this is equal to 0, but with un plus 1 equal to this signum, that is the sign of that there, that tells us that the expected value of the absolute value of the conditional expectation of xn plus 1 minus xn given fn is 0. But that is exactly equal to the L1 norm of that conditional expectation. And that means that this L1 random variable here is 0. And that's exactly what it means for xn to be a martingale, that this conditional expectation is 0 for every n. So we do recover the martingale-ness of the process xn under the assumption that the expected value of this stochastic integral is 0 for every n. Now, in the case where we're only assuming that it's non-negative or non-positive, we'll need a different argument here. For those, let's just fix a particular n and fix some measurable set in the sigma field Fn. Then we can take the process uj to be either 0 or 1, and it's going to be 0 most of the time. It's only not equal to 0 at the end time, where the end time is n plus 1, and there only if we're in B. Now, because we chose B in Fn, that means that this is going to be 0 until time n plus 1, and at time n plus 1, it's Fn measurable, which means that it's predictable. And when we calculate the stochastic integral, well, it's going to be 0 up until time n plus 1, because we're just adding up a bunch of 0 times delta x's. And at time n plus 1, it's just that last term, xn plus 1 minus xn times the indicator of B. Now, by our assumption, that means that the expected value of that is either positive or negative, depending which condition we're aiming for here. And therefore, that tells us that the expectation of xn plus 1 minus xn on the event B, which is that expectation of in plus 1 of u and b, has that fixed sign, either greater than or equal to 0 or less than or equal to 0, depending which case we're considering. Now that's true for all b in Fn. And therefore, we can conclude that the conditional expectation of xn plus 1 minus xn given Fn also has that same sign, which is exactly to say that we are a submartingale or a supermartingale as desired. And that concludes the proof. Okay, that gives us a new tool in our arsenal to recognize martingales and to produce new martingales or sub-supermartingales from old ones, the stochastic integral. Now we're going to use it to help understand what happens when we stop a martingale or submartingale or supermartingale. And what I mean by that is the following. If I take an adapted process, xn, and tau, a stopping time relative to the same filtration that xn is adapted to, then we can define the stopped process, x tau n, which is still a process evolving in time, like this. X tau at time n is x at tau min n. That is, we let the process evolve until time tau, and then afterward, it forever stays in the state x tau. Now, this is perfectly well defined because tau min n is less than or equal to n. And so even though tau might take an infinite value, we're never going to see that in this process here. Now, the first simple observation I want to make is that if our original process xn is L1, the stopped process is also L1, which might seem intuitively clear, but let's actually prove it carefully here. The absolute value of xn tau is, well, we can write it this way. Xn tau is the sum, k going from 0 up to n, of the indicator of the event that tau equals k, xk. And if we take the absolute value of that by the triangle inequality, that's less than or equal to the sum of those indicators of the events that tau takes any particular value in between 0 and n times the absolute value of xk. And now we can just drop this condition here, which is less than or equal to 1, and show that that is less than or equal to the sum, k going from 0 up to n, the absolute value of xk. Now that's a very blunt estimate, but it's certainly enough to show that if xn is an L1 process, so is xn tau. And now that brings us to our first landmark result here, the optional stopping theorem, which says that if x is a martingale, so is x tau. And if x is a submartingale, so is x tau. And if x is a supermartingale, so is x tau. The way we're going to prove that is to construct x tau as a stochastic integral relative to x. And to do that, we're just going to use the trading strategy process, un being the indicator function of the stochastic interval from 0 up to tau. We just need to verify that that is a predictable process in order for us to conclude that the stochastic integral is a martingale, or submartingale, or supermartingale, as the case may be, given that this is non-negative. Well, to see that it's predictable, we can just write this indicator as 1 minus the indicator of the event that tau is less than n. But in this discrete time context, the event that tau is less than n is the same as the event that tau is less than or equal to n minus 1. This is manifestly fn minus 1 measurable, and of course so is the constant 1. And therefore this is a predictable process. So therefore, the stochastic integral Zn is a sub or super or just plain martingale, since the underlying process, xn, was that same kind. But we already did this calculation on the first slide. We can write out what this Zn is, the definition of the stochastic integral. So that's the sum, j going from 1 up to n, of the indicator that j is less than or equal to tau of xj minus 1. That is, we're doing this telescoping sum, j going from 1 up to tau min n. And that just gives us exactly x tau min n minus x0. So the stopped process here is not quite equal to a stochastic integral. After all, stochastic integrals always have mean 0, and there's no reason to think that xn or xn tau did, but the only difference is the value at x0. So this is equal to Zn plus whatever x was at time 0. Zn is a martingale or submartingale or supermartingale, and it's easy to check that adding on a fixed f0 measurable random variable doesn't change that status, which concludes our proof of the optional stopping theorem. Now we're going to have lots of reason to celebrate and use the optional stopping theorem, and one of them is to prove the next result, which is another landmark result that is extremely computationally useful. It really is the comparable statement for martingales to the strong Markov property. Remember, the definition of a martingale is a process such that the conditional expectation of xt given fs for some smaller s is just the process at time s. That was for a fixed time s and t, but what if we want to use stopping times? And the optional sampling theorem says you can. If you condition x tau on f sigma, then you just get f sigma. But we have to be a little bit careful because there are some technical conditions that are required here. Sigma and tau have to be stopping times, and for this statement of the theorem, they also have to be bounded stopping times. In other words, there must exist some fixed deterministic finite time n such that tau, the larger of the two stopping times, is less than or equal to n, almost surely. Then, if xn is a martingale, or a submartingale, or a supermartingale, we will get that the conditional expectation of x at time tau, given the sigma field at the random time sigma, is equal to x sigma almost surely, or less than or equal to if we started with a submartingale, or greater than or equal to if we started with a supermartingale. It's very important that we include that boundedness assumption there. It can't be removed, as we'll see on the next slide. But that's not an impediment to using this to prove things about situations where the stopping times you are interested in are not bounded. A typical kind of way we'll use this, and you'll see on your homework, is to fix some capital N and use the stopping time tau min n, which is of course less than or equal to n. Prove the result you want using the optional sampling theorem. and then use one of our nice limit theorems like the dominated convergence theorem or the monotone convergence theorem to let n go to infinity at the end of the day. Now, this is a super useful result here, this optional sampling theorem, and let me show you one simple way that it is most commonly used. For example, we can just take sigma equal to 0 here. In that case, what the optional sampling theorem tells us is that x tau conditioned on f0 is almost surely equal to the random variable x0 at the beginning. In particular, if I take expectations of both sides, then that tells us, by double conditioning, that the expectation of x tau is the expectation of x0. In other words, our property that martingales have constant expectation even holds if we evaluate the martingale at a stopping time, provided that that stopping time is bounded. And you're going to use this fact on your homework to prove all sorts of things about the distributions of some important stopping times. This tends to be a tool used to understand the stopping time. We're going to prove the optional sampling theorem now using the optional stopping theorem. We start with our process xn, which is a martingale or sub or super martingale. Then we know that x tau, the stopped process, is also a martingale or a sub or super martingale. Now, we're making the additional assumption here that our stopping time is bounded, so let's let n be a bound for it. Tau is almost surely less than or equal to n. That means that if I take the conditional expectation of x tau given f little n for some fixed time little n, well, first of all, since tau is less than or equal to n, there's no harm in just writing that as x tau min n, conditioned on f little n. And that, by definition, is the conditional expectation of the stopped process, x tau at time capital N, given f at time little n. And the optional stopping theorem tells us that that is equal to, in the case of a martingale, less than or equal to, in the case of a submartingale, or greater than or equal to, in the case of a supermartingale, x tau at time n min capital N. That's true for every n less than or equal to infinity, even if we wanted to define the process at infinity. So that tells us how to condition on fn at a fixed time, but we know how to condition on a stopping time as well. That was the topic of lecture 45.3. That is, if we have any L1 random variable y, we turn it into a regular martingale process by conditioning on fn. Then, to condition that y on f sigma just means to evaluate that process at time sigma. In other words, we sum up over all n less than or equal to infinity of the event that sigma equals n, the conditional expectation of y given fn. So we just now apply this with y equal to x tau. And now, using what we learned above here, that is either equal to, greater than or equal to, or less than or equal to, term by term, the sum, the indicator of the event that sigma equals n, of just x tau at n min capital N. But that's the definition of evaluating this process at n equal to sigma. Well, that's just x at tau min sigma min capital N. And since tau is less than or equal to n and sigma is by assumption less than or equal to tau, that's just x sigma, which is the statement of the optional sampling theorem. Now, before we sign off on this, let me note that the boundedness condition simply cannot be dropped in general, and the typical counterexample will be afforded by perhaps our favorite martingale and Markov chain, the symmetric random walk. If xn is a symmetric random walk on the integer lattice, we start it at some point x, and we might be interested in when it gets to some point y. That is, what's the expected value starting at x of the process at the time hitting time of y? Well, of course, that's a no-brainer. At the hitting time of y, the process has hit y. So x at tau y is just y. On the other hand, starting at x, the expected value of x0 is x, because x0 is just constantly equal to x in that probability measure. And if the two states x and y are not equal, those two are not going to be equal, which means that the optional stopping theorem can't hold true here applied to that stopping time. Why not? Because as we showed, that stopping time is not bounded. In fact, it has infinite expectation. So that might seem like a bit of a bummer that we can't use this powerful theorem to analyze stopping times of nice processes like random walks. Well, that's not true, because if we're careful, we can cut off those stopping times, apply our arguments, and take limits. And you're going to use that on your homework to fully understand in many interesting cases the distribution of stopping times like tau y here.